So it's 5 o'clock Central European time. It's late afternoon over to the in the Pacific, or even late evening, I would say. And good morning to those that are on the west coast of the US and everyone in between. So welcome to this for the year, the last session of the Calling All Systems Engineer. Sorry, it says systems, but we are addressing systems engineers. This is a series of panel discussions hosted by INCOSE, bringing thought leaders together from around the globe. The series is sponsored by Dassault Systems, and we have the pleasure to have Representative Papke on board for the panel. This particular session is sponsored by SPEC Innovation. So also we have Steve Dam with us today. So looking forward to having this discussion. Today's topic, future of systems engineering, of course, a very vast topic. So I'm really happy and privileged to have a panel that can bring much light to this topic. 1 hour is really short, of course. It would give us just a quick glance of this, but so let's just jump directly into it. And before that, let me introduce our panelists shortly. So we have Dr. Erika Palmer, who's currently the Systems Engineering Program faculty at Cornell University. She's also the Deputy Technical Director at the International Council of Systems Engineering, INCOSE, as we are hosting this, and founding chair of the Social System Working Group at INCOSE. Erika's research and teaching focusing on the modeling and simulation of social technical systems and the policies that goes across different domains and their application. So she's going to bring a bit of a maybe wider perspective than usual. We have Barry Papke from CATIA Magic. Barry Papke is the MBSE Special Project Lead for CATIA Magic. He has 35 years of systems engineering experience and operations analysis experience in the aerospace and defense industry across the entire systems engineering lifecycle, from concept development through the integration, test, and post-delivery support. He's a member of the INCOSE Agile and Security Working Groups, and also part of the MBSE initiative. And then we have Steve Dam, an ESEP, Expert Systems Engineering Professional, and President of the SPEC Innovations. Been involved in research, experiments, operation analysis, software development, systems engineering training for more than 40 years. He was much involved in the C4ISR architecture framework and written books on the DODAF, the Department of Defense Architecture Framework. As I said, he holds an expert systems engineering professional ESEP certification from INCOSE, where he's also been acting as the president of the San Diego chapter and the Washington metropolitan area chapter, and also a past president for the Americas, as a director for the Americas, I should say. And finally, but not least, we have Bill Miller, who can now count more than 50 years of experience in the conceptualization and engineering of communication, information technologies, products, and services. He's a life member of the IEEE and senior member of INCOSE. He also a former technical director and currently the editor-in-chief of Insight, our practitioners magazine, and the leads the INCOSE FuSE Future Systems Engineering Initiative. So I would also like to thank, of course, the Honor Linda, the marketing and communication team that sort of are helping us behind the scenes here to make this happen. So with that, I think we just start with the first question here. I was wondering, I mean, just looking back over the last 30 years since INCOSE was established, and I can see that systems engineering has evolved from a focus on the development stage for a single system, mainly defense, to a discipline where actually we now have a model-based approach to cover complete life management of a system and system of systems, talk product lines in many different domains, such as transportation, automotive, healthcare, and more. Do we really need to evolve this further? Is it not just enough where we are today? Steve, what would you say to that? Do we really need to?
Oh yeah, yes. We've tended to focus on software heavily in software-centric systems, and that's all good. But there's a lot more we have to look at and broadly, and we need help doing that. It's a very hard job. The things we have to look at across the entire spectrum in terms of all the abilities, particularly reliability, maintainability, availability, survivability, on and on and on, that actually requires a much bigger view of things. And so this is where the technology may be able to help us in generative AI, particularly, because it can look across that broad data set and help us answer questions and look for problems that then help us do a better job of systems engineering.
Okay, so you're talking about that there would be more additional problems. I know, Barry, you have some concerns about some of the problems that we need to focus on for the future.
Yeah, I think one of the interesting things that have happened is that the number of entities continues to increase. You know, I know back in the 90s, if somebody said sustainability, you know, I wouldn't care. And here now we have the issue of cyber survivability as well as other survivabilities. We have needs for sustainability. We have socio-technical interaction, and then even we're bringing in other disciplines integrated into systems engineering because of now the digital engineering and model-based systems engineering transformation that before were separate silos, where that data now needs to become part of the authoritative source of truth. An example of that would be parametric cost estimation. You know, cost is really a property of the system, an attribute of the architecture, and so that needs to be brought in. So I think we've got new chapters to write in the INCOSE handbook to cover all of these new disciplines that before we, you know, generally weren't part of.
Okay. Well, you mentioned social technical systems, and just as I read the background of Erika Palmer, Erika, what's your take on this?
Hard for me not to jump in once I hear the word socio-technical. I think there's an important distinction that we need to make when you bring in this like evolve and expand of systems engineering, and it's the distinction between like evolving and expanding the domains in which we're applying systems engineering versus the different topics that we're addressing within systems engineering itself. Because then I'm hearing, for example, what is systems engineering doing itself versus what it's being applied to. And so, for example, you know, when we have socio-technical systems, that's something that systems engineering is now doing versus a new domain in terms of its more formal capabilities of, you know, and that can then be used in systems engineering practice. For example, modeling and simulation, building actual like simulators that account for, you know, a broad range of social concepts that can now be quantified. And so, but when we bring in things like expanding the domains in which systems engineering are applied to, we see things like then we're doing this for like environmental sustainability, or then social sustainability as an actual, like, we care about poverty and we want to use systems engineering to then try to address that. We care about, you know, not destroying our, you know, planet Earth. So we're using systems engineering to try to help, you know, help us with sustainability. But I want to make sure that, like, when we are, you know, we say evolving or expanding, what exactly are we evolving and expanding? Is it the domains or the topics?
Okay. Well, and I think is that something we can already look at the trends. I mean, Bill, as an editor of the Insight, and also, of course, having a long experience, do you see specific trends here?
I'm sorry, do I see what? Trends?
Specific trends in terms of, you know, evolving and expanding.
Yeah. So I'm actually going to answer that by taking a back to the future approach in response. So my professional history actually started at the old Bell Telephone Laboratories, and systems engineering was being done in earlier stages and evolved from the 1920s through to the modern era. One of the references by an engineer from Radio Corporation of America back in 1957 identified system engineering as having two requirements that are pretty broad. First, a determination of the objective that is to be reached. And second, a thorough consideration of all factors that bear upon the possibility of reaching the objective and the relationships among those factors. And so a broad definition that, cost, human systems, emerging technologies, environmental, sustainability. I still kind of view that old definition that's very broad as more and more factors are need to be addressed, especially these days as the scale of systems, everything's interconnected or interrelated in some way to everything else, that the world is not deterministic. And we have to address uncertainty and account for that so that the systems we produce are, I believe a relevant term is these days, used to be called robust, but resilient. And that we need to anticipate and be prepared to address emergence factors that come out of these systems, the unintended. Now, emergence can be good things, but it could also be something not good in terms of that. And how do we look forward and address those?
And just to then tie something that you just said, Bill, into what's going on in the chat, Bruno from France is then talking about, like addressing complexity. And when I hear the word, I know there's a complexity definition more in the systems engineering community, and I'm not going to touch that in this session. But what I want to say, when you're talking about emergence of these different unintended consequences, and then how we're actually evaluating emergent properties of systems as we go forward, I think is an excellent thing for us to keep in mind.
Right. Thanks, Erika, for that. And an important aspect of this is too often system engineering can be narrowed down to a small thing. So different organizations, different cultures might say, oh, okay, system engineers are responsible for the requirements. That may be one piece. In my own professional experience, it's been a much broader role in terms of looking at emerging things coming out of research. In fact, perhaps nudging things in the research area to get them mature, to be able to deploy them to deal with foreseen advances that we need to be able to make through the whole development cycle, the operation cycle, all the way through decommissioning. Oh, another important piece in terms of modeling and simulation. Actually, I'll use the term characterization. I believe we pay insignificant attention to the ecosystem in which our systems operate. We need to characterize those in much more depth. And also recognize that when we place systems, they're at the effect of the ecosystem, but our new systems affect the ecosystem.
Right. Yeah, and I think that's something that's, of course, this system, and that kind of just keeps expanding. But so what can we do? I mean, what kind of, and I say use the word now, tools, which would of course be wider than just software tools, but what can we use? I mean, maybe this is something for Barry and the EOS team if you look at tool side.
So one of the expansions of our modeling capability is enterprise architecture. Whereas when we talk about systems architecture modeling, we're looking at an individual system of interest, and what we're creating is a design of that thing. Whereas enterprise architecture actually addresses the evolution of the system over time, where it starts with here are the capabilities I have today. Here are the capabilities I need tomorrow. It includes planning how we're going to get there, pointing to what Bill just said. We need to determine, is there research needed because that helps our time phasing. We need to understand more about the operational context of our system before we look at its design. And then we need to involve and understand the impact of our systems on the organizations that are going to inherit them, and also understand who's going to build this stuff, how's it going to happen. That whole big cycle is called enterprise architecture, and it's yet another task that's becoming part of the systems engineering. I'm trying to decide whether to say workflow or workload. it's both.
Well, in fact, that's why I got involved with architecture frameworks back many years ago, was that they needed to take a systems engineering approach to that problem. And in fact, the enterprise architecture work, working on the panel, I worked on the C4 ISO architecture framework panel, and it was very obvious that what they were doing was systems engineering, just at the enterprise level. And in fact, all the framework products were simply systems engineering products. And we thought that by forcing people to actually, create these products, because they were overlapping and were actually pretty tightly integrated set of products, that they would actually do good systems engineering. We were absolutely wrong. They would go off and create view graphs still and do things like that. I worked on one big project where they actually decided to create a work breakdown structure and break it up by each of the individual products. It was insane. It was a great way to spend a lot of money, and they did, on an architecture. They spent $1 billion on an architecture.
Yeah, and it was interesting too, because back then those frameworks were built before there was a language to implement them in a tool, and it led to all kinds of.
So they were using Papke. They were using System Architect at the time, and it was still Papke, I think, or maybe I think IBM had just bought it. And so, yeah, they were using that tool, and they used it to some degree of capability. But the problem is they had 100 modelers, and trying to check in, check out databases, or moving the databases around, or merging the databases was a nightmare. And they wanted us. We had to redo that every week, and it took 18 hours to create a new build of the database that they could then put out to the modelers. So things like that.
How do we?
In the technology. We've gone way beyond that in technology now with cloud computing, that we can now create a simultaneous interaction of people on the cloud working together collaboratively. And that's a huge plus. Plus, now with the generative AI, I think we have the opportunity of taking and look at these mass data lakes of information and using that information to do a better job of bringing all these things together. But it still is up to us to make sure we do the people part of it. And that's the socio-technical that Erika was talking about. That's what's really kind of been almost always missing. And most of the time when I see people do modeling, the first thing I ask them, well, where's the operator? And they have, oh, yeah, we didn't model the operator. Well, the operator is the most important part of the system.
Well, thank you for bringing that up, because so I get equally frustrated as I see a lot of modeling work then isn't including people systems, right? Because and I think someone put it in the chat about good architecture is inherently lucky, right? Because a lot of what's going on is that if you're not including these people systems, then hopefully it's going to work out. and one of the reasons that I feel like there's not a lot of good training on how to do this on socio-technical systems yet. I mean, you're seeing it patchwork at different universities, and there's certainly no best practices on how to actually do system architecture of this stuff. So I feel in some ways that progress has really been slow, because I'm doing this one cohort at a time and spreading out, and most of my students are it's through a distance learning program, so they're already in industry, so it's a lot of defense and defense acquisition and stuff like that, where my students are coming from. And so those areas, I feel not just because they're my students, but I mean, just in general, these kinds of students coming in and getting systems engineering training on how to actually break these concepts, social concepts and people systems into system architecture, it's the slow stream. So I feel in terms of the future of systems engineering, we are getting there, but we also need more people teaching then the future systems engineer how to build this kind of architecture.
Could I break in there? Because, of course, we have the Smart Cities Initiative, which sort of tries to take a human-centric approach to, or not tries, it's taken a human-centric approach to looking at what is a smart city, and they are asking for all support from modeling. And I know there's a lot of modeling being done, but is your opinion, Erika, that we're not there yet in terms of, taking our current modeling and system modeling approaches to the level of dealing with social technical systems?
Well, I mean, like the actual methods are there, and you can do it if you know how. So I know that like it needs to evolve where it is now. I mean, all methods need to evolve. I'm not saying they're perfect, but what I am saying is even kind of the state of the art of how to do this, and like for example, could be implemented in smart cities. Like there's just too few people who are trained how to do this right now. And I mean, even when I'm going to, I mean, a lot of attention in INCOSE, thanks to me and some other people, and especially Smart Cities and Jen Russell and Marcel, who I see is also here today with Smart Cities, like are getting, a lot more attention on how to do this like socio-technical system architecture. And I think that like initiatives like that are fantastic because even those who are, past what they would consider when they would be getting training in systems engineering are seeing that other people are evolving what they're doing in terms of building system architecture for socio-technical systems, that then they're jumping on the bandwagon and adjusting their practice. So I am absolutely seeing progress, and I'm just really thankful for, those that are behind smart cities in order to, really push the practice of systems engineering forward.
Yeah, and you brought up, something a moment ago, Erika. This whole, because we're moving into this model-based paradigm. Oh, I used the word paradigm. I don't think I can do that. That's a bad word. This model-based environment. Having been doing model-based systems engineering for almost 30 years now, one of the things that we have is the skill set needed to be a good architect and to be able to model, to be able to translate things in the real world and in your mind into these abstract modeling languages. And that's definitely is that a nurture or nature task? And does it take certain people to be able to do that? Can everybody do that? I think that's a continued challenge as we move further into that domain. That particular skill set and aptitude is becoming more and more important, and more people are needing to do it than before.
But one of the things I recognize is that systems engineering is much more than just modeling and simulation. It's so many other things we do.
Yeah.
And we get ourselves a little wrapped around the axle with the modeling simulation from what I've seen. We're trying to move to what we're calling data-driven systems engineering, because what we want to do is get back to what's the data elements we really need to collect and use to help create information and drive decisions from. And if we can focus back on that a little bit and not so much on model, maybe we can do a little bit more of these other things. That's been kind of again, like you, Barry, I've been doing the model-based systems engineering since I've been doing systems engineering. First time I drew a flow chart was in 1971. So
yeah. And I think that's the real challenge is that when you talk about the model-based paradigm, it's not that it's model. It's that we now want to capture data in semantically with semantic meaning in digital environments where we can do this search. And it's about the challenge is about all the things that we need to represent. What's the right way to represent them? Where would they be? This gets you talked about the database problems and model architecture problems back, in the early days. We still have them today. We're trying to do so much now in this digital environment before we've actually kind of thought through, again, all the emerging results and emerging characteristics that happen when you do that.
That's one of the reasons we adopted cloud computing back in 2011, 2012. We first started doing cloud computing. Creating a cloud native platform allows you to have that common database that everybody can access simultaneously. And that gives us an incredible power of configuration management of the data. And that's to me one of the enabling technologies, because back in the 90s, we had this concept called net centricity, and we didn't have a good way to implement it. There was some kind of, there was this translator you had to create, the universal translator to move data back to these federated systems. And it was just a nightmare. And so cloud computing has given us the ability to do what we thought we could do, wanted to do in the 90s. And so we can do that today. But now we need to keep moving beyond that. Because again, I keep coming back to AI, because AI is probably one of the most exciting new technologies that's going on out there. The other is optical computing. I mean, that's another one that will be a big game changer when that becomes available. So I mean, some of these technologies can help us do and solve some of the problems we're trying to solve, because as you say, they're complex problems, Erika. They're this socio, and then now you're going to put in not only hardware, software, and wetware, you've got AIware. So you've got all of it that you're trying to orchestrate and make work together in a coherent fashion.
Topic of AI is something I guess we'll address shortly. But before we sort of leave the enterprise architecture, the architecting part, so to say, there's a number of questions in the chat. And I think a number of those sort of relates to where do we draw the boundary of MBSE versus enterprise architecting. Also, there's another question around where does integrated management systems fit into enterprise architecture. Third one, really looking at how do we see the seam between systems engineering and enterprise architecting in a model-based engineering paradigm. A lot of questions here, but I mean, I think there are a lot of terms in now. We have MBSE, enterprise architecting, systems of systems. Somebody will step up to the challenge and give.
Well, so I think the big problem is it's all systems engineering, and we keep trying to balkanize our discipline. We've got the problem right now in the off-sector defense at DoD here in the U.S. is trying to put together a program called Systems Engineering Modernization. And it's the idea of taking all of these different practices and integrating them together. Well, they never should have been split apart. They're all part of systems engineering.
Maybe a question to Bill then.
One of the challenges, in for example, enterprise architecture, is that enterprise architecture is not the responsibility of systems engineering. It's a distributed responsibility between the acquisition people that have the vision and the plan, between the users, the operations people that have to know how this is going to work in the world, the systems engineers for developing the systems, the project management people for planning it, and then the people responsible for organizations. It's a very distributed responsibility. However, almost none of those other disciplines have people that understand how to represent their concepts correctly in an architecture. And so it's this part where it may be a systems responsibility to develop and maintain all of this information, but they're not responsible, they're not the source of information. So now, again, we're starting to see how systems engineering is this kind of central hub of bringing this data together, but still needing to have everybody participate properly in the process and contribute their pieces. So I think that's a real challenge in making those things happen correctly.
Oh yeah, I totally agree, Barry, and that's one of the things that we've called it many things over the years. IPTs, we called it concurrent engineering. Yeah. You're all supposed to bring all the disciplines together and optimize across the disciplines. That's again part of systems engineering. It's been there since I have ever heard of systems engineering, and so it's something I think again we tend to want to stovepipe things because our heads can only get wrapped around so much stuff. And again, we need help. The tools have to help us.
I'd like to bounce this with Bill. What's your take on?
Well, a couple of things. Again, I said that my own experience base professionally was a much broader definition. And whether somebody is classified as a system engineer or something else is the thing that needs to get done being done. And is it being communicated and building a consensus within an organization to move forward, in alignment, as opposed to the intramural warfare that can occur when you have these different stovepipes and different definitions. So one of the big things is how do we bridge that? And again, over the course of my career, I had to be multilingual. I had to be able to speak marketing to marketeers. I had to be able to speak finance to finance people, business cases, all that kind of stuff. I needed to be able to speak mechanical engineering, electrical engineering, which I'm trained in, chemical engineering, and Steve, software engineering or software stuff also. And so, you know, you need to have a key attribute of a system engineer is being able to establish the communications channel for effective communications and to be often brokering that.
But it seems like our if you like stakeholders or the people we will need to talk to, engage, sort of gets wider and wider, and then sort of now we need to talk to business people more, get them more involved, and do the support them in doing the architecture, etc. Is that the case? I mean, Erika, I think that's, you know, probably even more a challenge if you look at the social technical systems.
Before Erika, I want to raise the thing we've been talking about, the human condition. So humanity exists on a spectrum of different knowledge bases, worldviews, belief systems, and you know, and so there's no one size fits all to this. That's an important characteristic we need to acknowledge and work with. Okay.
And then just to, you know, bring that together with something that Barry brought up earlier, and also something that I saw in the chat, is that there's, like, you know, not only is there not one size fits all here, I've been asked repeatedly for, like, what is the one way that you can model, you know, social concept X, and then we can put it into an SML library and blah blah blah. And I'm like, that's not how this works. You know, everything winds up becoming incredibly bespoke when you're trying to do this. Like, so this is for enterprise architecture, but also when you're just doing any kind of you know, socio-technical system modeling. If you're looking at how you are going to, you know, bring teams and communities together to actually engineer systems and then literally create that system architecture, that's going to be different per project. How then a specific piece of technology is going to be, you know, and then here I'm talking about system architecture, how that's going to be embedded in one particular environment, to come back to the ecosystem comment that Bill had in the beginning. That changes not only in terms of different contexts, but it changes at different points in time in the same context. And so when you're looking at this thing, like, and we're talking about then model governance came in this, we're not building the one model to rule them all. Sorry for the Lord of the Rings reference there, but what we're doing is we are creating models to, when it comes to the socio-technical part, we're creating models then to actually analyze specific dynamic problematic behaviors that we're trying to address in the systems engineering lifecycle. And because you're using modeling in that very specific way as part of systems engineering process, not using model-based to replace what is the system engineer, to also point out something that came out into the chat. And the reason why I wanted to come back to Barry's comment and is about, like, well, is this something that is trained, or is it just some people are good at this? I think that people have, like, a natural inclination to be able to break this stuff up into system architecture. But, like, I can also just tell you in the classroom, nobody is good at this, like, until they practiced a ton. And my students hate being terrible, like, publicly, and, like, drawing things that are terrible and get picked apart. But that's, like, literally how it's done. I joke with my 13-year-old, like, you know, like playing Mario. Everybody dies in Mario. That you're going to do a terrible job until you do a great job. It just takes a ton of practice.
I'd like to pile on that thread with actually something that very much concerns me, that I'm in the future of systems engineering. I know when I first started, you know, in MBSE, what I found was the act of translating the real world into this abstract world and modeling it and making sure that model represented what we meant. I found I understood more about that system than anybody. You know, and what concerns me about AI is that we're trying to make so many things easy and fast. To me, I think the systems engineer's most important role is knowing the why. We've made a decision. Now another decision comes along that's either impacted by that or impacts something else. And we're the ones that have to make the trades. Therefore, we have to know the whys.
Oh, yeah.
And when I start seeing people say, let's automate this, let's automate this, let's automate this, I think automation of the manual clerical parts are great, but we got to make sure that the intellectual judgment decision-making part is still a human process. Because as soon as the systems engineer no longer can answer the why, I mean, that's how Skynet got started, right? As a joke, right?
Exactly.
So I think that's something that very much concerns me when we start talking about AI. Is we're because of the problem with the skill set. Oh, we'll solve that skill set. We'll make AI do it. We don't have to train anybody. Oh, that's the death of this. I mean,
that's silly. And that's a silly thing that people expand it to. No, I look at our AI as an intern who's going to do a lot of my legwork for me, and then help bring the information to me so I can make the decisions. And I've got to ask them the right questions. I've got to task them correctly. If I don't, I'm going to get garbage back. And that's true today with the generative AI. It's really true today with ChatGPT. It'll hallucinate on you. And that's what they call it, hallucinate. I call it lying. But you have to understand what you're dealing with there, and you're working with it and having to help you do a better job. But it's that access to all that data that's we're really struggling with. And certainly I know I struggle with it every day in my head. All of the things I'm supposed to be doing simultaneously is beyond my capacity. So I have to realize I have to rely on other people historically, but now with the AI, maybe I can rely on that also a little bit more too.
Would not the AI sort of help us and even make us a little bit unemployed? Do you think? I mean, but that's could it not bring together all that information? That's the systems engineering role today. What do you?
No, there's still so much for us to do. Are you kidding me? No, there's no way that's going to happen, because really access to that information will just help us do a better job of doing the job we need to do. Yeah. One of the problems we have is all these system failures, right? Everybody recognizes that. That means that we're not doing our job well enough. And we need help to do that. You can't do it with a small team of people or one or two people. And how many projects get more than one or two systems engineers?
Yeah. So it seems a little bit that we've been talking about for quite some time, is that we system engineering needs to step up. I mean, understand the context, which becomes larger and wider as we evolve the discipline, and then really get to the point to understand why we're doing things, what's the real problem, and then we still have our engineering body that's sort of gonna look at providing the right solution to that problem, and then integrate engineering disciplines and all that. So maybe that's the way we're going forward. But there's been some discussion within INCOSE, I think, over the years, that we're losing a bit touch with the engineering part. What would you say on that, Bill? I mean, that we sort of not get really connected with the core, if you like, engineering, where we actually create the technical solutions.
Well, there's a lot of spirited conversation that goes on within COSE. We have 50 plus working groups, several initiatives, and as you might expect, people in working groups tend to look at it from the perspective of their working group. And one of our major challenges, and it's something that it's been recognized for some time, is how do we get cross-fertilization across the working groups to get I'll invoke a NASA term called best balanced design. So we have all these stovepipes, and how do we, make it much more, I can't think of the right word right now, but yeah.
Well, optimize. Bill, it's optimization, and that's what part of our job.
Yeah.
To me, that's one of the basic parts of our job. In fact, you gave the definition of it. The second one you laid out that we used earlier on. That is exactly that optimization that we're supposed to be doing, and we're not doing it. We're not doing it well enough. Again, if we hyper focus on software and saying software is the problem, we're going to spend all our time worrying about the software. We're going to miss all that other stuff. And that's what worries me. And I see that happening.
Yeah. But Barry, for example, I know that your company is sort of looking at how you connect the systems engineering tools with the engineering tools, the traditional, more disciplined mechanicals, electrical engineering. Is that, what's happening? How is that evolving? What do you see in the future on that part?
Yeah, that's actually still a challenge today. There are there's a lack of standards for tool interoperability. I know System LV2, is going to try to solve some of that. I think, well, that's their objective anyway. But it's really a challenge. I've talked about this several times in other papers, and what we're doing here is we're taking what used to be a manual process of people putting the information in their head in a document, handing a document to somebody else, that person reading it, translating it into their tools, and now all of a sudden, we need to have this automated flow of real-time data exchange, between the tools. I don't in my world, in the airborne ISR world, the mechanical and aerospace engineers were responsible for the airplane structure and the installations, and they knew what the airplane could provide in terms of power and cooling and weight and vibration protection and things like that. And the systems engineers were, responsible for the parts that made the plane heavy, which was all the gear, and the mission stuff in the back. And it was the systems engineer said, "This is what I need," and aero guy said, "This is what you got." And it was a negotiation. Well, I need to put it here. Well, I can put 1,000 pounds in the nose, but it can only be as big as a bowling ball. And we fought through those give and takes of how do we get how do we fit all of this stuff in there and still have this airplane airworthy? And that required constant data exchange between, as the mission systems were evolving and we're making new technical decisions about what to do, it affects the installations and things like that. The problem of making sure that the guys designing the installations knew what we were still putting in the airplane was a constant battle. And that's what we want to solve with this digital engineering environment. But that involves us actually, guess what? We have a systems engineering problem. We have to design a giant information processing system that manages engineering information. And by the way, it's a heterogeneous distributed system that, by the way, is a systems of systems, because Aero changes their tools independently of systems engineering, independently of software engineering, independently of program management, yet we still expect them to talk. That problem of starting to get the data exchange and data semantic relationship problem out of the way is a huge problem right now for the industry, in my opinion. Some people can solve it if they develop both sides of it, but when you don't, guess what? You got to negotiate, and it's a challenge.
Yeah. And Barry, I think you're absolutely 100% right about that, and that's one of the problems that we've seen. People are trying to kludge together all these tools to make them work together, which they've never been designed to work together, and sometimes maybe they shouldn't be integrated. One of the things we've done in our research is realize there are times to integrate with the design engineering tools, and there are times not to. There's having that interface between, maybe I want to run that finite element analysis and get all that data, but the only data point I need at the systems level is a distribution. That's all I need. I'm going to use that, but then I want to curate that other information so I don't lose it. And that's the other trick, is being able to tie those together so we don't lose the information. But you don't have to fully integrate the tools. It doesn't even make any sense interoperability-wise. One of my early experiences was at Los Alamos National Laboratory. We had 2 physics codes we used that worked in 2 totally different time regimes by orders of magnitude in time differences. And it made no sense to integrate the 2, but they spent 10 years trying to do it and spent probably millions of dollars. And the designers who were using the tools said, I don't need that. I've got the ability to do the right physics in one tool, then generate a file it passed that to the other tool, and it does what its physics is supposed to do. That's all I needed. And so it doesn't make any sense. Sometimes it doesn't make sense. So that's part of the problem we have to get into, is the detailed level of when does it make sense to integrate and when does it not make sense to integrate.
Yeah, and that was exactly my point. Talk about going back to the future. Everybody remember LISI, levels of systems integration? Level 1
Yes.
manual, level 5, I mean, we got to decide, is it okay to have an intermediate format, or does this need to be real time? It's an architecture of this system. And like you said, you can't just, it's not one size fits all, one approach fits all. We have to understand how this affects the engineering life cycle and what we really want out of it. Yep.
Mm-hmm.
But would we still conclude that there's some hope here that we'll get some languages and data formats that will actually support at least the the exchange, and also make the connection between the systems and the more specialized engineering tools?
So we think we're using one. It's called Lifecycle Modeling Language, and we've been using it for 10 years now, and it works very well. It's very simple, easy to understand, and easy to work with, and it's an open standard. It's available for anybody to use. In fact, I think it actually says on the Wikipedia page that they use it or can use it. And so that's great. We need that common ontology, underlying language to do this. And again, it's even more than ontology. It's really kind of a combination of ontology and graph theory. But that's the kind of real language elements we need to be able to pull together. We need nouns, verbs, adjectives, and adverbs in some structured way to bring that information together, that we can then disseminate it and make sure it can interoperate. And I think that's the easy way we can do this kind of thing. But again, people have to go and use it.
Yeah. So actually, that's I think to Erika, and actually I think the people issue here is probably also how do we get people to talk to each other, not just machines.
To your original question here, which was about bringing the engineering part back into systems engineering, because and then answer that from a very socio-technical system perspective. And then the fundamental nature of engineering is to build something to transform the world in some way, right? But I feel like, and I know from the community of people that are pushing this opinion, is that when we need to put the engineering back into systems engineering, it's more about bringing more formal modeling and simulation and more hardcore quantification of different processes that we're bringing, and optimization and things like that into a systems engineering environment. And so, from the first part, I think that, if we really are going to be building something to transform the world in some way, all of us can maybe argue that what we're doing does that. It's the nature of engineering. But if it's to the former, when it comes to socio-technical systems, and we're talking about things like optimization, I always like to say that optimization for socio-technical systems is not really possible because of the mountains of uncertainty that come with socio-technical systems. And even if we happen to not have any uncertainty in those systems, we are, and you're able to actually come to the one true correct answer, and in terms of formally determining the optimization. It will almost certainly be directed towards optimizing towards one specific stakeholder group while marginalizing the others, and then it becomes an issue of ethics. So I always joke that if you can optimize, or if you try to optimize in socio-technical systems, you'll be very precise, but you will be precisely wrong because of that uncertainty. And even if you were precisely correct, you will have some moral and ethical dilemmas to take charge of. But in terms of interoperability of socio-technical, or the people part of what we're and bringing the socio-technical systems into system operability, I will say that doesn't mean that we can't do, systems engineering of these people systems. This is why we actually do the formal modeling and analysis of it, even if optimization is really not possible. And we do that through policy simulators. Policy is the control systems of socio-technical systems. Policy systems, however, do not control anything. They only influence in order to direct the trajectory of different systems towards some sort of desired outcome. And when you're then working with policy systems and you want to use systems engineering to actually have that be the thing you're developing to transform the world in some way, that's why we build then these policy simulators so that you can create policy scenarios to see how these will play out.
Mm.
Oh yeah, Erika, I've worked at the policy world for many, many years here in the DC area, so I totally agree with what you're saying, and I've applied model-based systems engineering approaches to that all this time, and it's amazing how easy it actually would help. In fact, I would suggest that we get Congress to take it on and use it to do traceability of all the laws too. That would be very helpful. So that we
Good luck with that.
Well, I think we need to move into political engineering then. So.
Well, I mean, I think we actually, within the working groups, we have the lawmaking working group, right? That's actually looking at this from a system point of view. So, you know, actually, we like to ensure that we cover some of the questions here. And I think there's one that really sort of attracted my attention. And I think maybe we could have a round the table on this one, which is from Boggs Nishek. Sorry if I pronounced that wrongly. Systems engineering is in flux. What are the success criteria for systems engineering as a discipline that it needs to achieve? That's his personal statement, that we are in a bit of a flux. I guess that's, you know, that we can do really great things in the future, or we could stay where we are. Or what are the success criteria we need? So who would like to go first on this one?
I would also say this is probably a plug for the FuSE initiative, Future of Systems Engineering, since we're getting towards the top of the hour here, it might be a good way to segue into that, is that to say, part of, and I'm Bill and I are the lead team for that initiative. And, through that, we are developing, KPIs for systems engineering. How do we know that we're actually innovating? Are we innovating because what we're doing, we think is interesting and is pushing the boundary? How are we actually even able to measure that? So that's part of what we're going to be bringing out in 2024.
Yeah. I actually read the question very differently. And
okay.
What it made me realize is something that's been unfortunately absent from our discussion, which is test and evaluation. When you say what's the criteria for systems engineering, it's that we've delivered a system that fulfills its intended use in the operational environment. I mean, at the end of the day, that's the success criteria. And what we haven't talked at all about in any way is how all of our FuSE initiatives, what this means to both development testing and to operational testing. And by the way, I think testing is an area where AI may have a huge positive impact on what we're doing. They're already doing a lot of that already with the automotive autonomous driving stuff. The only way you can test all that stuff is through some AI initiatives. But I think that's a big part of it. We have to ask the question, to me, the criteria is, what are we doing that ensures that that our systems do their job in their operating environment the way they're supposed to? By the way, now doing things like, okay, so how do you test cyber survivability? I mean, these are really complex problems that we're going to need to challenge.
Barry, we have been nudging on the question, and in 2024, hopefully early, you should see, early to mid, you should see some things regarding how we go about doing that. One thing I want to key back to Erika mentioning the KPIs. In the SE Vision 2035 document published by INCOSE back in January 2022, in chapter 4 on how realizing the vision, there's published a roadmap with various areas, research competencies, methods, tools, applications, and so on, with bands for 2025, 2030, 2035. From my perspective, 2025 is like tomorrow. But when I look at all the goals for each of those bands, I regard them as too fuzzy. it's a good statement to get started, but we need things that are measurable to determine have we made our marks or not, and also trending. Are we going to meet our marks? And so that's a big part of the effort moving forward.
Yeah. So in fact, test evaluation is something I've been actually talking about quite a bit lately. There's a T&E is a continuum article, if you want to get out of ITEA, that's quite good, that Chris Collins wrote. He's the director for developmental test and evaluation at OSD. And so their idea is, make it a continuum of doing back and forth. So you test a little, build a little, test a little. Of course, that's always been a philosophy, but this is one they're trying to push. The other is to recognize that the software world's already doing that. Our software guys, when they write a new feature, a new set of software, they will write the test case for it at the same time. And so they build those automated tests so that they can do the testing quickly. We need to do the same thing. We should be thinking, as we're building the high level requirements, how are we going to get that bought off? Where is it? What's the operational suitability of that requirement? How do we show that that's going to meet the customer's real need? And we should be thinking about that immediately, as opposed to letting that be something that goes downstream.
Great. There's much to talk about this, and I think our time is running out, but maybe a final little one. What are you going to do just after this, before Christmas, on yourself to enhance the future of systems engineering? What is your current focus? Bill,
I'm going to train my children. I'm going to train my children to develop systems thinking skills as I put them to work to do all the different holiday tasks that need to get done.
All right.
Yeah, so
I thought you were busy with setting up the international workshop in January.
No, it's, you said over the holidays. Over holidays.
Oh, okay. For me, my perspective, Tom, I've got two threads. Teeing up Insight magazine. Well, actually, I'm editing the December issue right now, which is focused on system engineering advances research at French universities. So that's December, but then teeing up things for 2024 and beginning planning for 2025 for Insight magazine to be supportive of the future of system engineering. And within the future of system engineering, Erika and I have this charge over the various streams of future system engineering and various projects. The streams, in fact, addressing one of the Dharmesh's comment about competencies. One of the streams is foundations. Another stream is methodologies. Third stream, application extensions. And then an overall stream in terms of refinement of the vision, because we published in January 2022, but we're not clairvoyant out of the box. We're learning, and that vision needs to be refined. And also part of that fourth stream is more detailed roadmaps that are measurable, so we can assess progress and be nudging things along.
Right. Steve, what's your current focus?
Lots of things. I just, by the way, put a link in the chat for the Systems Engineering for Kids book for Erika, so you can use that to help you with your kids expressing why they need to use systems engineering. It is a free ebook. Anyway, so the things we're working on right now, we're trying to get ready for our next release, which is coming up in January. Version 4.9 of the tool is one of our main goals. I have just tons. We have a webinar coming up. Santa is a systems engineer, done by our interns. So it's actually going to be very entertaining. So a couple things like that going on.
So everybody gets what they need and getting the right product in the right way. That sounds great. We're counting on you for that.
For me, I'm actually working in some of the one in the FuSE, the FuSE security under Rick Dove's security working group. I'm supporting that. And then another FuSE initiative is the complexity definitions as a foundation by Ali Devek. And the third thing I'm working on is trying to possibly bring another thread into FuSE, which would be bringing parametric cost estimation, into the systems engineering lifecycle. And interestingly enough, a number of us have recognized that the things that Ali says he's using to measure and quantify system complexity are actually the very things we measure and quantify in the COSISMO parametric cost estimation language. And so there may be some parallels there that can actually help realize what Ali's trying to do. So I'm actually having fun. I no longer manage the solutions team. I'm now getting to be an individual contributor, and having a lot of fun doing that.
Yeah, Barry, I think we need to cut our panel short here, and we can continue afterwards. But we reached the top of the hour. Again, an hour is short for talking about the future of systems engineering. We would like to, of course, invite everybody to get involved. Check out the INCOSE working group, the Future Systems Engineering Initiative. Reach out to us and we'll connect. Attend the international workshop in January if you have got the possibility, either there in person or online. And with that, I would like to conclude this the last session of the Calling All Systems Engineers 2023, but the series will continue in 2024, so welcome back. And last but not least, thank you, panelists, Eric, Barry, Bill, Steve, a lot for sharing your thoughts about the future.